My name is John Barris, and I'm a Global Business Development Manager at AWS working on AI and machine learning solutions. You're very likely here because you're interested in machine learning and specifically fast, automated decision making. Today we'll be talking about Amazon EC2 Inf1 instances used for high-performance machine learning inference. More ML happens on AWS than anywhere else. From large enterprises to startups, AWS has over twice the number of machine learning-based public references than any other provider. AWS's focus on invention allows our customers to move from evolutionary improvements to revolutionary innovations. This happens when they leverage their vast industry knowledge coupled with AI/ML to think of ways to bring new products, new categories, and even new businesses to market. Now, companies are working with us to build solutions that are core to their business. For example, Convoy, a Seattle-based logistics company, is building their entire company and value proposition on machine learning. The company is disrupting today's inefficient trucking model by automating it using machine learning. Convoy has created a machine learning matching system to provide better matches for shippers and truckers, allowing them to move freight more efficiently and lowering costs for both parties. Cerner is tapping into AWS's deep portfolio of machine learning and AI services to surface insights that will help their healthcare provider customers streamline operations and provide more personalized patient care. They've already developed a model that predicts congestive heart failure up to 15 months before clinical manifestation. Pairing this predictive tool with real-time integration to individual health records can support provider decision-making in real time. Now imagine you are a social media or photo sharing company that ingests 1 billion images per day. You classify those images by content, perhaps grouping the photos by individuals or identifying the subject of the photos to make them searchable. Now, even if you're able to correctly classify 90% of those images, 1 billion images per day, that still leaves 10% or 100 million images per day unlabeled. Every single percent of improvement correctly labels an additional 10 million photos per day. Data scientists and ML researchers work hard to improve their inference algorithms, and usually this comes at the cost of making larger and more complex models that require more time and computation. In some settings, inference comprises 90% of the infrastructure spend for developing and running machine learning applications. Now, this is the motivation for the development of the AWS Inferentia chip. AWS Inferentia is a custom ML chip entirely designed and built by Amazon to solve one problem incredibly well. Inferentia is a high-performance, lower-power inference workhorse. Each Inferentia chip has 4 neuron cores, and each neuron core has a high-performance systolic array matrix multiply engine. An Inferentia chip provides up to 128 TOPS, also called teraops or trillion operations per second. The Inferentia's low power draw allows us to pack 16 chips into a single server, and this one server can provide more than 2,000 TOPS, or 2 petaops. Each neuron core has a 2-stage memory hierarchy, a very large on-chip cache, which reduces the need for swapping data in and out of external commodity DRAM. Reduced precision computing is faster for 2 simple reasons: bandwidth and compute. There are fewer bits to move into and out of memory, and fewer bits to calculate. CPUs typically use 32 to 64-bit floating point for high-precision calculations. FP16 uses 16 bits to represent floating point numbers by reducing both the precision and the range of the number. BF16 reduces the precision, but not the range compared to FP32, and this is important for maintaining the quality of results in machine learning inference. For some types of inference, 8 bits provide sufficient range and precision. Inferentia supports all 3 reduced precision data types, int8, FP16, and BF16. Now, not all machine learning models are small enough to fit in a single chip. Inferentia has fast chip-to-chip interconnect that allows up to 16 chips to operate in unison for large, high-performance models. A high-performance race car is ineffective when confined to urban streets full of stop signs, narrow streets, and signal lights. A fast chip like Inferentia must be surrounded with a specially engineered, frictionless architecture to reach its full potential. That is why AWS designed a custom high-performance server that overcomes networking, memory, and file system bottlenecks. In the Amazon EC2 Inf1 instances, AWS Inferentia is connected to AWS custom second-generation Intel Xeon scalable processors. It is also paired with AWS Nitro, which accelerates virtual machine networking and file system performance. Now within the server, the Inferentia chips are connected by a custom high bandwidth chip-to-chip network. Each Inf1 instance supports up to 100 gigabits per second networking for low latency, high throughput, and end-to-end inference performance. The EC2 Inf1 instances support AWS Neuron, a new software product that natively integrates into popular machine learning frameworks and optimizes the performance of Inferentia chips. Inferentia is also integrated with all popular ML frameworks, namely PyTorch, MXNet, and TensorFlow. Small batch optimizations improve performance as it allows achieving max performance under strict response time requirements. The higher sustained utilization using batch size equals 1 is achieved through a combination of large on-chip cache and various power optimization techniques like zero skipping, and will enable continued neuron performance improvements over time. The Inf1 instances are optimized to serve a variety of machine learning inference use cases like image classification, object detection, natural language processing, speech recognition, search, ranking, and fraud detection. These use cases are the backbone of inference workloads in enterprise and startups alike. Users who are looking to increase their ML application performance and reduce the cost of running these models can select EC2 Inf1 instances, and we expect that lowering the cost and improving the performance of machine learning workloads will be a major driver in ML adoption, providing a better experience to end users. There are 4 Inf1 instance sizes to choose from, depending on the types of workloads you're running. Image classification and some NLP, or natural language processing workloads, perform well on a single Inferentia chip with a small number of vCPUs. The Inf1.x large is a good choice for these types of inference workloads. For object detection like YOLO, you may require additional CPU power or RAM, leading you to choose a 2x large instance. Now, both the XL and 2XL instances provide access to a single Inferentia chip and up to 25 gigabits per second networking. As your models increase in size and complexity, you may choose an instance like the 6x large or 24x large, which provide access to 4 or 16 Inferentia chips respectively. Now, since each chip has 4 neuron cores, the 24XL instance can support models which run on up to 64 connected neuron cores. The 24XL instance also supports 100 gigabit per second networking and 19 gigabit per second of EBS bandwidth. Inf1 instances are also supported in AWS managed services such as Amazon SageMaker, Amazon EKS, and Amazon ECS. Now let's talk about the software ecosystem. AWS Neuron is the SDK providing tools and drivers to develop, deploy, and profile Inferentia accelerated inference applications. It is designed from the ground up to allow for maximum scalability and optimizing both the highest throughput and lowest latency for a wide variety of use cases. Neuron has 3 main components. It has an ahead-of-time compiler, a runtime driver, and profiling tools. The ahead-of-time compiler can take a pre-trained model and convert it to a Neuron binary file which can be loaded and run on the Inferentia chip. The runtime driver allows you to load and execute ML models, and the profiling tools help you identify bottlenecks and fine-tune your models for maximum performance. Neuron is pre-integrated into popular machine learning frameworks, including TensorFlow, MXNet, and PyTorch. It supports commonly used machine learning models, including ResNet for image recognition and classification, and BERT for natural language processing and translation. If you already run applications through one of these frameworks, either on CPU or GPU, using the Neuron SDK will seem familiar, and minimal code changes will be required to move your application to Inferentia. Neuron is pre-installed in our AWS Deep Learning AMIs, or you can pip install it into your own AMI. Instructions are available on GitHub, alongside other detailed tutorials, technical briefs, and reference manuals for those who wish to fine-tune their applications. In most cases, though, we see customers change a few lines in their framework to enable Inferentia and start running their inference applications. Now, I'd like to cover a few important capabilities that were designed to allow developers to focus on optimizing their applications and scale inference workloads as seamlessly as possible. The first example is called Smart Partitioning. Smart Partitioning automatically optimizes neural net compute and decides what part of the model graph will run on the Inferentia chips and what parts are more suitable to execute by the framework. AWS Neuron is aware of the system resources and is able to partition the neural net graph intelligently, so that the most demanding compute operations run on Inferentia, while other operations that run more efficiently on the CPU end up partitioned to the framework. Now, this system capability is a pragmatic approach to running inference workloads in the cloud and allows developers to fully utilize the system and increase overall performance. Now, many developers told us that although training models in FP32 is time-consuming and expensive, the advantage is that it provides the best accuracy. But 32-bit compute is expensive and high in power consumption, and it's really hard to move to lower 16-bit floating point or integers to optimize cost. Well, this problem is solved with Neuron's capability we call FP32 automatic casting. AWS Neuron and Inferentia are the first ML accelerators in AWS that can take a trained 32-bit model and run them at speed of 16-bit using bfloat 16 data types. This conversion happens automatically in hardware and is enabled by default. It allows you to keep your high-precision trained models and seamlessly run high-throughput inference, enjoying the speed and lower cost of the 16-bit data types. Users already report back that the inference accuracy is only reduced by a fraction of a percent for the models they run, so we encourage you to try it out. Now next, let's talk about Neuron Core Pipeline. Customers that are running real-time inference applications like search or voice assistants are constantly looking for ways to increase the throughput, but keep the latency of each inference call low, so they can maintain a high level of interactiveness with the application end users. Using a batch size of 1 typically solves the latency constraint, but it does come at a high cost because running one inference call at a time yields low throughput and low utilization of the hardware that leads to higher costs. With Neuron Core Pipeline, the entire model will be stored on the cache memory attached to each neuron core. Neuron cache memory is about 5 times faster than the latest available HBM that you typically see with GPUs. Neuron intelligently shards the model across multiple neuron cores and can scale up to 64 neuron cores on our largest instance size. Once the model is fully loaded into the cache, Neuron runtime starts sending the inference calls that in turn stream across the neuron cores. Each core calculates its part of the model and passes the results to the next neuron core. From the perspective of a user, once enabled, all the available neuron cores in the system will appear as one large virtual device to the framework. So from the framework level, it's completely transparent. On the other hand, neuron core groups enable application builders to concurrently deploy multiple models to optimally use the hardware resources by running different models on each of the groups. It's very flexible, allowing you to optimize the hardware utilization very well. You can run the same model in parallel on multiple neuron cores, or run separate models on groups of 1 or more neuron cores. For example, when different neural networks need to run as a pipeline of a given input, like is usually the case with applications that require decoding and encoding data, users can define groups in different sizes to fit their pipeline execution flow. And this feature is used by Alexa text-to-speech, which will be detailed later. So here's an example of building and deploying an Inferentia workload in a popular ML framework. You can see that adding the, setting the model up to run on the Neuron SDK simply requires adding a few lines of code, importing the TensorFlow.neuron, and then compiling the model using Neuron. And AWS Neuron is integrated into Amazon EKS, Amazon ECS, Kubernetes, and AWS Deep Learning AMIs. You can also install AWS Neuron in your own AMI container if you prefer. But since it's so simple to build and deploy using these frameworks, you're able to maintain portability between hardware platforms. Now, Inferentia is also supported in AWS managed services, so you can use AWS SageMaker for building, training, and deploying machine learning models, and it even provides a one-click deployment of models onto Inferentia and Inf1 instances. Let's talk about price and performance briefly. So if you're running an object detection workload like YOLO v4, we have an example here of running YOLO v4 model end-to-end with TensorFlow. And when I say end-to-end, what I mean is the activations or the image coming in the network at one side and then the result being expressed in the network on the other side. So this isn't just a synthetic speed test, but actually a full workload test. And as you can see, we compare a G4DN instance with a NVIDIA T4 GPU with an Inferentia Inf1 instance. And you can see for object detection with the YOLO v4 that it's almost 90% higher throughput, and the total cost for doing inference on Inf1 is 37% lower. Another example is using BERT large with TensorFlow, a sequence length of 128 for natural language examples, natural language processing like using language translation or sentiment analysis. And you can see here in this case that Inferentia has a 38% higher throughput and is almost half the cost of the G4DN instance. Finally, one final example is with image classification using ResNet 50, where the performance is 25% higher and the cost per inference is 45% lower. So as models grow in complexity, they become too slow for CPUs and too expensive for GPUs. Inferentia enables customers to improve their ML decision-making while keeping costs under control. Let's consider an Alexa example for text-to-speech conversion. Alexa supports real-time conversations, and with over 100 million Alexa devices in the field, responsiveness is one of the most important requirements. The conversion of the phonemes to a low-quality voice in the text-to-speech process uses a model that is bound by processor-to-memory bandwidth and is enhanced by Inferentia's on-chip cache. Upsampling the low-quality audio to high-quality speech requires 90 billion calculations per second of speech, and improving the performance of the model allows the system to scale while keeping the size of the infrastructure under control. Here's an overview of how the Alexa service works. When the Alexa identifies a wake word, it captures the utterance following the wake word and sends it to the cloud service. So for instance, if you say, Alexa, what time is it? What time is it is recorded and sent to the cloud service. Now, we use a speech-to-text system to convert the recorded speech to something that can be used by the computer. And then that's sent to a system that understands, using natural language understanding, identifies the intent of the user and what they're asking to do. And then that intent with the parameters detected in the natural language, that's sent to a skill, which then responds with a directive about what words to play. Those words then pass through a text-to-speech algorithm, and the high-quality speech is sent back from the cloud service to the Alexa device, and so that you can carry on a conversation. So in a little bit more detail, the text-to-speech is translating input text to the output speech signal. And this is realized by two major components: context generation and speech production. Now, context generation is translating linguistic representation of the input, like phonemes, to acoustic representation of the speech. It employs sequence-to-sequence models since the inputs and outputs have different length. And the output of this model is a low-resolution representation of speech, which includes the voice, speaking style, and accents, and is represented by a Mel spectrogram. The next step is the voice production model, or neural vocoder, which converts acoustic speech representation to actual speech signal. Output speech signal is sampled at 24 kilohertz to produce high-quality sound, and it involves upsampling 300 times the acoustic representation, and is achieving high quality because achieving high quality is computationally intense. The Amazon Alexa team migrated a majority of their GPU-based machine learning inference workloads to Amazon EC2 Inf1 powered by AWS Inferentia. At Alexa, they do billions of inferences every week, so they are always looking for ways to improve the end-user experiences and boost performance and reduce cost. As of today, we've got 80% of Alexa voice responses synthesized using the AWS Inferentia-based Inf1 instances. They're seeing a total 30% cost saving over GPU-based instances, but for longer sentences, they achieve up to 65% cost savings. We've also seen a 25% reduction in latency compared to GPU instances, and this has been a critical improvement for us as it results in faster Alexa voice responses and enables us to innovate further on Alexa's voice. Alexa Voice Assistant is using... Now, I just want to give some examples of users who have selected Inf1 instances for production. And as you can see here, we have a number of startups and large companies, including Autodesk, Snap, Anthem, Condé Nast, and we also use Inferentia in Alexa and Amazon Rekognition. So just some examples. Snap is, they employ machine learning throughout Snapchat, and one of their goals is to improve efficiency and performance. and they're focused on improving performance and cost. And they started with recommendation models and are adopting more models with the Inf1 instances in the future. And Autodesk has an AI-powered virtual assistant called the Autodesk Virtual Agent, which uses a natural language understanding model to answer over 100,000 customer questions per month. And they're able to obtain a almost 5 times higher throughput over G4DN for their natural language understanding models. Now, for Anthem, they have a number of customers that they use an application to automate the generation of actionable insights from customer opinions using deep learning natural language models or transformers. And Inf1 instances provide twice the throughput compared to GPU-based instances and allow them to streamline their inference workloads and control their inference infrastructure. And Condé Nast, they have 20 leading media brands, and they're able to integrate a recommendation engine with AWS Inferentia chips. And this means that they observed a 72% reduction in cost compared to previously deployed GPU instances. So you can also, I mentioned Amazon Alexa already, and with Inf1 instances, they've been able to lower their operating costs by about 65% for long sentences and 30% overall. And then Amazon Recognition supports analyzing billions of images and videos daily. And with object classification, they can reduce increase their throughput and reduce their latency by a factor of 8, and the throughput by they can increase their throughput by a factor of 2. So you can try EC2 Inf1 instances today. They're available in AWS regions, including US East, US West, Asia Pacific, and Europe, and South America. And like the rest of the accelerated compute instances, the Inf1 instances are available in the standard EC2 purchase options, including on-demand, reserved, and spot pricing options. They're also available as part of the EC2 savings plan. So customers who have application dependency on NVIDIA libraries can continue to use G4 for good cost per inference, but the rest of the customers either running on G4 or on CPU today would get the best performance and lowest cost by using Inf1 instances featuring Inferentia. Thank you.